Imagine a world where your most sensitive data, your financial records, your medical history, even national secrets, is completely unhackable. Not just difficult to crack, but fundamentally impossible to break, even by the most powerful supercomputers of the future. This isn't science fiction anymore. It's the reality quantum encryption is building. And in this video, we'll reveal exactly how it works. So, what's the big deal with our current encryption? Why do we even need something new? Right now, most of the internet's security relies on what's called public key cryptography. Think of it like a digital mailbox. Anyone can drop a message in your mailbox using your public key, which is like the address. But only you have the special private key to open the mailbox and read the message. This system is based on difficult math problems, like factoring huge numbers. For current computers, these problems are so hard they take thousands, even millions of years to solve. Your bank transactions, your private messages, they all rely on this mathematical fortress. For now, it works. But here's the problem. A new kind of computer is on the horizon, the quantum computer. These aren't just faster versions of the computers we use today. They operate on the bizarre and wonderful principles of quantum mechanics. While a classical computer bit is either a 0 or a 1, a quantum bit, or qubit, can be a 0, a 1, or both at the same time. This property, called superposition, along with another called entanglement, gives quantum computers the power to solve certain problems exponentially faster than any classical computer ever could. And one of those problems? Factoring huge numbers, the very foundation of our current security. An algorithm called Shor's algorithm, designed specifically for quantum computers, could shatter modern encryption in minutes, not millennia. Everything we thought was secure would be laid bare. This isn't a distant threat. It's a ticking time bomb for digital privacy. The race is on to build what's called a post-quantum world, a world with security that can withstand a quantum attack. This is where quantum encryption, or more accurately, quantum key distribution, QKD, enters the picture. It's a complete paradigm shift. Instead of relying on math problems that are hard to solve, QKD relies on the fundamental laws of physics. And that's what makes it unbreakable. Let's break down how this works. It all starts with photons, individual particles of light. In QKD, we use these photons to create a secret key between two parties. Let's call them Alice and Bob. Alice sends a stream of photons to Bob, one by one. Each photon is encoded with a bit of the key, a 0 or a 1. She does this by setting the polarization of each photon, which is basically the direction the light wave oscillates. She can polarize it vertically, horizontally, diagonally, or anti-diagonally. Here's the clever part. Alice randomly chooses between two different sets of polarizers to encode her bits. For example, she might use a rectilinear set that's vertical and horizontal, or a diagonal set. For the rectilinear set, a vertical photon could mean 1 and a horizontal one could mean 0. For the diagonal set, one diagonal could be 1 and the other 0. Bob, on the receiving end, also has to measure the polarization of each incoming photon. But he doesn't know which set of polarizers Alice used for each photon, so he has to guess. He randomly switches between his rectilinear and diagonal measurement bases. After the entire stream of photons has been sent, Alice and Bob get on a regular, open communication channel, like the phone or internet. This part doesn't need to be secure. They compare notes, not on the bits themselves, but on the type of polarizer they used for each photon. For the instances where Bob guessed the correct polarizer set, his measurement will be accurate and the bit is kept. For the instances where he guessed wrong, the measurement is random and useless, so they just throw that bit away. For example, if Alice sent a vertically polarized photon to represent a 1 and Bob measured it with his rectilinear detector, he'll correctly read a 1. But if he happened to use his diagonal detector, he'd get a random result, either diagonal or anti-diagonal, with a 50-50 chance. They discard these mismatched measurements. What's left, after they sift through all the results, is a shared, secret key, a random string of 1s and 0s that only they know. This key can then be used with a one-time pad, a classical encryption method that is mathematically proven to be unbreakable, as long as the key is truly random and used only once. Now for the real magic, the part that makes this unhackable. Let's say an eavesdropper, we'll call her Eve, tries to intercept the key. She wants to catch the photons from Alice, measure them, and then send identical copies on to Bob so no one knows she was there. This is where the laws of quantum mechanics step in to save the day. The no-cloning theorem states that it's impossible to create an identical copy of an unknown quantum state. Eve can't just copy the photon, so her only option is to measure it herself. But here's the catch. The act of measuring a quantum particle inevitably disturbs it. This is known as the observer effect. When Eve measures the photon, she has to guess which polarizer set to use, just like Bob did. No matter what she does, her measurement will alter the photon's state in a detectable way. When Alice and Bob compare a small sample of their final key, they will find discrepancies or a higher than expected error rate. They'll know someone was listening. They can then discard the entire key and start over, leaving Eve with nothing but useless, partial information. Physics itself becomes the security guard. Any attempt to eavesdrop is like trying to read a letter written in disappearing ink. The very act of looking at it makes it vanish. So, what does this mean for our future? Is everything about to become quantum encrypted? Not quite yet. While QKD is already being used in some high-security applications, like banking networks and government communications, there are still challenges. The biggest one is distance. The signal, those tiny photons, degrades over distance. They can get absorbed or scattered by the fiber optic cable. Right now, the practical distance limit for QKD over fiber is a few hundred kilometers. Researchers are working on solutions like trusted nodes, which act as repeaters, and even satellite-based QKD to create a global quantum network. China's Mishia satellite has already successfully demonstrated this, sending entangled photons between ground stations over 1,000 kilometers apart. This is a huge leap forward towards a secure global quantum internet. The cost and complexity of the hardware are also hurdles. The single photon detectors and emitters are still expensive, specialized equipment. But just like with classical computers, which once filled entire rooms and now fit in our pockets, the technology is advancing rapidly. Components are getting smaller, cheaper, and more efficient. Companies and research institutions around the world are pouring billions into this field, driving innovation at an incredible pace. We're also seeing the development of quantum random number generators, which are essential for creating the truly random keys needed for secure encryption. Unlike software-based random number generators, which are ultimately predictable, these devices harness the inherent randomness of quantum phenomena to produce numbers that are physically impossible to predict. The transition to a post-quantum world will be one of the most significant technological upgrades in history. It's not just about protecting your messages. It's about securing the entire infrastructure of our increasingly digital society. Think about self-driving cars communicating with each other, smart grids managing our power, and vast networks of Internet of Things devices. All of this will require a level of security that is fundamentally unbreakable, a level of security that only quantum physics can provide. While the road ahead has challenges, the promise is clear. A future where our digital lives are protected not by complex but breakable math, but by the immutable laws of the universe itself. The quantum revolution in cybersecurity isn't just coming, it's already begun. Thanks for watching. If you found this journey into the quantum world fascinating, be sure to hit that like button and subscribe for more deep dives into the technology that is shaping our future. And let me know in the comments, what other quantum concepts would you like to see explained? See you in the next one.